The vacuum of space is not absolute. Within the low Earth orbit, LEO environment, a tenuous whisper of atmosphere persists. This invisible resistance exerts a constant, relentless force upon every satellite, every debris fragment, slowly but inexorably dragging them downwards. It is the silent threat of orbital decay. Orbital decay is the process by which an orbiting object loses altitude over time. The primary catalyst for this descent is atmospheric drag, caused by the friction between the spacecraft and the residual atmospheric particles at altitudes typically below 2,000 kilometers. Each encounter saps kinetic energy. Even at altitudes of several hundred kilometers, where the atmosphere is incredibly thin, the immense orbital velocities of spacecraft amplify the effect. A satellite traveling at 7.8 kilometers per second encounters a significant number of molecules, creating a cumulative braking effect that reduces its orbital energy. For active satellites, this drag necessitates continuous orbital adjustments. Onboard propulsion systems fire periodically, expending precious fuel to boost the spacecraft back to its designated altitude. This process, known as station keeping, directly limits a satellite's operational lifespan. The sheer number of objects in LEO exacerbates the problem. Thousands of operational satellites, along with millions of pieces of defunct hardware and mission-related debris, populate this critical zone. Each object is subject to the same relentless pull, leading to predictable trajectories of decay. As objects decay, their paths intersect with increasing frequency, escalating the risk of high-velocity collisions. Such impacts generate even more debris, creating a cascading effect known as the Kessler syndrome. This scenario threatens to render vast swaths of LEO unusable for future missions. The LEO environment is humanity's most accessible and vital orbital domain. It hosts communication satellites, Earth observation platforms, and the International Space Station. Its continued viability is critical for global connectivity, scientific research, and national security infrastructure. The rate of orbital decay is not constant. It fluctuates with variations in atmospheric density. Solar activity, specifically solar flares and coronal mass ejections, can heat Earth's upper atmosphere, causing it to expand. This expansion increases atmospheric drag, accelerating the descent of objects in LEO. A satellite's physical characteristics also dictate its decay rate. Objects with a high surface area to mass ratio, such as large, lightweight, defunct solar panels or insulation fragments, experience greater drag. Conversely, dense, compact objects resist drag more effectively, decaying slower. The life cycle of a decaying object culminates in atmospheric re-entry. As the object descends into denser atmospheric layers, frictional heating intensifies. Most smaller debris fragments and even some satellites disintegrate completely, burning up in a fiery spectacle across the night sky. Larger, more robust components, however, can survive re-entry, posing a terrestrial risk. Uncontrolled re-entries of rocket stages or defunct satellites necessitate predictive tracking to assess potential impact zones, though the vast majority fall harmlessly into the ocean or unpopulated areas. To mitigate this, active missions increasingly incorporate deorbiting strategies. This can involve using residual fuel to perform a controlled re-entry over a designated ocean impact site, or maneuvering into The economic impact of orbital decay is substantial. Shorter satellite lifespans due to increased fuel consumption for station keeping translate to higher operational costs. The need for constant replacement or upgrade cycles strains budgets for both governmental and commercial space endeavors. Strategically, the proliferation of decaying debris creates a persistent geopolitical challenge. An accidental collision between national assets could be misinterpreted, leading to diplomatic tensions. Maintaining LEO as a safe operational zone requires international cooperation and adherence to debris mitigation guidelines. The mitigation of orbital decay and debris proliferation is a global imperative. International bodies and space agencies are developing new guidelines for satellite design, mandating deorbiting capabilities. This includes methods such as propulsive deorbit, electrodynamic tethers, or passive drag enhancement devices. Propulsive deorbit maneuvers involve using a satellite's remaining fuel to lower its perigee sufficiently, ensuring atmospheric re-entry within a specified time frame, often 25 years. This proactive measure prevents defunct satellites from lingering as long-term hazards in crowded orbital paths. Electrodynamic tethers offer a novel, fuel-free alternative. These long conductive wires interact with Earth's magnetic field, generating a small electromagnetic drag force. This force steadily reduces the satellite's altitude, guiding it towards a controlled atmospheric disposal without propellant expenditure. Passive drag devices, such as deployable sails, increase a satellite's surface area, intentionally accelerating its orbital decay. Once a mission concludes, these sails unfurl, magnifying atmospheric resistance and ensuring a relatively swift, uncontrolled but predicted re-entry. Beyond deorbiting, concepts for active debris removal, ADR, are under development. These ambitious projects aim to retrieve or deorbit existing large fragments of space junk that pose the greatest collision risk. Technologies include robotic capture, arms, nets, or even laser ablation systems. The comparison to terrestrial challenges highlights the unique difficulty of space. Unlike oceanic pollution, where gravity assists cleanup, objects in LEO maintain extreme velocities. Any intervention must match these speeds and address the vacuum and radiation of the orbital environment. On Earth, industrial waste can be contained or recycled, but in LEO, every discarded component becomes a ballistic projectile. The sheer scale of orbital mechanics means that even a small bolt can cause catastrophic damage, a risk far exceeding typical industrial hazards. The degradation of LEO infrastructure due to orbital decay offers a stark contrast to terrestrial depreciation. A bridge on Earth might require maintenance over decades, but its fundamental structure remains. In LEO, the fundamental existence of an object is perpetually challenged by the orbital mechanics and inherent unavoidable decay. Without proactive measures, the long-term viability of low Earth orbit faces an inevitable collapse. The increasing density of active satellites and defunct debris amplifies the probability of catastrophic collisions. Each new fragment accelerates the degradation, creating a self-perpetuating cycle of environmental breakdown. The theoretical concept of the Kessler syndrome represents this ultimate failure point. A sufficiently high density of objects could lead to a cascading series of collisions, generating an exponential increase in debris. This would render specific orbital altitudes and potentially the entire LEO environment impractical for sustained human activity. Such a collapse would cripple global telecommunications, weather forecasting, and Earth observation capabilities. The loss of critical infrastructure in space would not only impact daily life, but also severely impede scientific advancement, national security, and humanity's understanding of its home planet. Innovation in space, particularly for next-generation satellite constellations, is heavily reliant on accessible LEO. If this domain becomes too hazardous, the cost and risk of deploying new systems would become prohibitive, stifling advancements in areas from global internet access to asteroid defense. Economically, the collapse of LEO represents an untraceable loss. Billions of dollars invested in existing space assets would be jeopardized. Furthermore, the future economic growth anticipated from the burgeoning space economy, from tourism to resource extraction, would be severely curtailed. The constant tracking of millions of orbital objects, many too small to precisely catalog, becomes an increasingly complex and expensive endeavor. Radar systems strain to monitor fragments down to a few centimeters, but countless smaller, yet still destructive particles remain undetectable threats. The geopolitical implications of a congested LEO are significant. As nations and commercial entities launch ever more satellites, the competition for valuable orbital slots intensifies. This generates complex diplomatic challenges regarding resource allocation and the management of shared space infrastructure. Space traffic management has evolved into an incredibly complex undertaking. It demands sophisticated real-time tracking systems and predictive modeling to anticipate collision risks. Operators must constantly coordinate collision avoidance maneuvers, an energy-intensive and time-consuming process for active satellites. A persistent ethical and economic dilemma revolves around responsibility for legacy debris. Many fragments originate from missions decades old, launched by entities that no longer exist or under different regulatory frameworks. Who bears the cost and responsibility for cleaning up this historical space? Junk remains largely unresolved. This ongoing orbital degradation stands in stark contrast to the seemingly infinite expanse of the cosmos beyond. While humanity gazes at distant galaxies, its immediate celestial doorstep, LEO faces a finite capacity problem, a bottleneck for all future space endeavors. Yet, Humanity's initial ventures into space, from scientific observation to commercial enterprise, are entirely confined to this fragile shell. Preserving its accessibility is not merely an environmental concern, but a foundational requirement for any deeper exploration or utilization of extraterrestrial resources. The irony is palpable. As humanity dreams of establishing outposts on Mars or mining asteroids, its immediate space environment faces a self-inflicted crisis. The very ambition driving space exploration generates the waste threatening its future. Our technological prowess, capable of precisely guiding spacecraft across astronomical distances, simultaneously risks rendering our own orbital backyard unusable. The silent force of orbital decay, amplified by human activity, highlights a critical intersection of physics and foresight. The challenge of orbital decay transcends mere engineering. It becomes a fundamental test of humanity's capacity for collective, sustainable stewardship. It is a critical lesson in managing shared resources not only on Earth, but also in the vast, unforgiving vacuum of space. The development of sustainable space practices, from responsible satellite design to robust deorbiting mechanisms, is no longer optional. It is a fundamental requirement for maintaining the orbital pathways that enable global communication, navigation, and environmental monitoring systems essential to modern life. The sheer volume of projected launches, particularly massive satellite constellations, underscores the urgency. Without stringent adherence to mitigation strategies, the very ambition to expand humanity's presence in space risks sealing off its most accessible frontier behind a barrier of its own making. This ongoing struggle against orbital decay is a constant reminder that even in the vastness of space, resources are finite and human actions have profound, far-reaching consequences. The delicate balance of Leo demands perpetual vigilance and innovation to avert an irreversible crisis. Thus, the future of humanity's access to space hinges not just on technological advancement, but on collective responsibility. The challenge of orbital decay compels us to consider not merely how we will reach the stars, but how we will responsibly preserve the very pathways that lead us there. How will future generations judge our stewardship of the cosmic commons?